chapter 9F, which is conditional probability. Okay, so if you've done year 10 last year, you would have done an exercise on conditional probability. And I think for many of you, that exercise in year 10 would have been the most complicated exercise. Okay, it doesn't get any easier in maths methods. In fact, it gets more complicated because there are more equations that will be set out to you as well. Now, our learning intentions is to introduce or reintroduce conditional probability and the way we write its notation. And we're going to relate the probability of some event A with its intersection with B and the conditional probability with B using a rule, and it's called the multiplication rule. The multiplication rule is similar to the addition rule. It's just a rule where you can use it when the opportunity arises, but we're going to be looking at how we get to the rule so you understand why it works. The success criteria can identify problems involving conditional probability and apply conditional probability and the multiplication rule to solve problems. So let's reintroduce conditional probability. Here's an example of a table where you list out all the results of rolling 2 dice. So this would be die 1, that's die 2, and you've got combinations of results. You can work out probabilities for this. For example, what's the probability of getting at least one odd number? Okay, and all you have to do is count up all the results that are odd and divide it by the total number of outcomes in the sample space. How many outcomes are in the sample space?
36.
36, right? Because 6 times 6. Yeah, you're the first person in the video. So it is something out of 36, and we can calculate it. But if we want to give a condition to that question, let's say, for example, I'm only interested in the rolls where at least one of the dice is odd if my first outcome starts with 6. Okay, my first die roll is 6. That's going to mean I'm going to ignore most of these outcomes in my sample space, and I'm only going to focus on the ones that start with 6. Okay, the probability of getting an odd number if, I'm not going to write out the notation yet, if the first roll is 6. How many outcomes are in my sample space now?
6.
It's less, it's reduced because you've given a condition to it. So now it's going to be out of 6, and I'm not going to be lazy and I'll actually count out which ones are odd. So there's 1, 2, and 3. It'll be 3 out of 6, which is 1/2. So that's the key. Conditional probability is where you give a condition on your events. And what that does is it reduces the sample space. It makes it smaller. Here's the question, I'll read it out. It's not a question that you need to work on first. 2 dice are tossed. What is the probability that the sum of numbers exceeds 10, given a 6 on the first die? Once again, you're tossing 2 die, but you're not going to, I'm going to jump back a bit, you're not going to list out the entire sample space because you're only interested in some of those outcomes. And the condition to that is given a 6 with the first dice. So one way we can list out the outcomes is just to write it out. So if event A is 6 on first dice, as a set, I can write it as 6, then 1. That means getting a 6 on the first die and 1 on the second. Then 6 and 6. Okay, close it up with set brackets. Now my question is, what is the probability that the sum of numbers exceeds 10, given this condition? Exceeds 10. The way I'd write it out, using proper notation, is the probability that the sum of numbers exceeds 10, that's B, given the condition for set A is satisfied. How many of these outcomes exceed 10?
2.
2.
3. No, 2.
2. Good. So it can't be 10, but exceeds 10. So that'll be 2 out of a reduced sample space. 2 out of 6, which turns out to be 1/3. Okay, I'll repeat it one more time. Conditional probability is related to reduced sample space. And the way you know how your sample space is reduced is through this condition. That's usually worded as given. So here's the notation for conditional probability. The probability of event A given a condition B. Because you know that you've got a reduced sample space, it's going to be based on how you've reduced it. That's the condition. So you're going to be, is it the other way around on the slides? Yeah? Okay. I'll switch it around. Doesn't really matter, but you need to write it the correct way in your equation. So if A is the condition, you divide it by the probability of A. Okay, that reduces your total sample space. And at the top, we have the probability of both of them occurring at once. So the probability of B happening given A has happened must mean both of them must be happening at the same time. That means, in our previous example, a number exceeding 5, as well as having a 6 on the first row. And you divide it by the reduced sample space. Okay, there's a special note there. I'll explain this. If you write the condition the other way around, it's not going to be the same as your previous question, equation. And the way it's different is that your conditions changed. Previously, your condition was A, now your condition is B. The numerator of the fraction is still the same, but you're dividing it by the other event. Okay, so you must never mix these up. Okay, this other part, if you've got complementary events in your conditional probability, like our previous condition was rolling a 6 on the first die, the complementary event could be not rolling a 6 on the first die, but it still works in the exact same way. You just put dashes in the correct positions in your conditional probability formula. So I'll write that down as well. If you've got the probability of A given not B, that's going to be the probability of A and not B divided by the probability of not B. Just put the dashes in the correct places. Okay, in the next slide, we're going to introduce the multiplication rule. The multiplication rule is just your conditional probability formula that's rearranged. Okay, and here's how you rearrange it. It's written at the bottom. The probability of an intersection is equal to the probability of A given B multiplied by the probability of B. Any guesses where we got it from? Saka?
The equation.
The equation up the top?
No.
I think for this.
They rearranged it.
Yeah, they rearranged it. I think they rearranged the second
Yeah, that's
equation by multiplying the probability of B on both sides. It's the same equation, but we give it a special name because it's so important. So I'll write it down in another colour. This is the multiplication rule. And the multiplication rule states that you can figure out the intersection of two events if you know the probability of event A given B multiplied by the probability of B. And it's just rearranging our conditional probability formula. We're going to be using that in a few of our examples in a moment. In this slide, there's a tree diagram. And you've actually done this multiplication before when you're working on a tree diagram. So on a tree diagram, you list out your different stages. So A is stage 1, and B is stage 2. And the event that happens in stage 1 can happen or not happen. And the event in stage 2 can happen or not happen as well. So when you place probabilities on these branches, which you've done in previous years, what you're actually giving are the probabilities of your event in the first stage. And the probability on your second branch is based on what you got as an event in your first branch. I think it's worth illustrating this through an example. Let A be drawing a heart first, and B be drawing a heart second. Okay, the standard deck of cards, 52 cards, and you're drawing 2 cards out. The first branch would be drawing the first card. What's the probability that your first card would be a heart? Any guesses? Out of 52, how many hearts are there? 13, right? So the probability of A is 13 out of 52. The probability of drawing a heart second is then going to be based on whether you got a heart first or not. If you got a heart first, you're going to have 1 less heart to choose out of the remaining 51 cards. So the probability of getting a second heart, given that a heart was drawn first, is going to be 1 less heart and 1 less in total. Okay? Your tree diagram is actually a conditional probability, but we've just never stated it that way. Now, here's the question. What's the probability of getting both a heart first and a heart second? What you generally do is multiply these together, don't you? Multiply along the branches, that gives you both happening at once. This is exactly the multiplication rule. It's just the tree diagram restated as an equation. So for some of these questions that you'll do in 9F, you can also do them and get the correct answer using the tree diagram, but I hope you can see that if you know this formula, it's much more efficient. A standard die is rolled, so you're only rolling a die once. Find the probability of rolling a 6 given that an even number is rolled. They haven't given us any letters to represent these events, so we should define some letters. Let A equals, you already have that on your sheet. Let A equal, rolling a 6. Let A be roll a 6. And B roll is even. I'm going to ask you to copy this down as I do this on the board. I can tell it's a conditional probability question because I can see the word given. Okay? And that tells me that there's a condition that's being placed on my probability. Now for these 2 events, we can actually list out the different outcomes, which are 6 and even. So rolling a 6 means there's only 1 outcome in that set. And getting an even number means that there are 3 outcomes in that set. 2, 4, and 6. Okay, it's a standard die, so there's no numbers greater than 6. Now, when it's your turn to calculate the conditional probability of getting a 6 given that the roll is even, you're only considering this reduced sample space. So you reduce sample space. There's 3 outcomes in there that could be equally likely. But only one of them is what's going to make your experiment a success. So that's the 6 out of 2, 4, and 6. And that's it. You've done your first question in conditional probability. Okay? Once again, I'll repeat. There's that reduced sample space because you've got a condition there. Yeah, you got a question?
Why is it 1 over 3? You sort of just skip a little bit of working out. Is that okay to do?
Are you talking about the multiplication?
Yeah, so I'm talking about the middle one in black.
This one?
Yeah, would you have to write out the whole thing?
Okay, good question. I was just about to get to it.
Yeah.
Thanks for thinking ahead about this. We actually haven't used this formula So we can actually do the same question with the formula. It's going to make it a little bit more complicated,
Yeah.
but that formula works with any kinds of questions with conditional probability. So let's split up our space like what I've done, and we'll try and use the formula this time around. A given B is the same as the probability of the intersection divided by the probability of your reduced sample space.
Yeah.
So what we've got to do if we want to use the formula is know what the probabilities of the intersection are and what the probability of B is. And like I said, it's a little bit more complicated. So let's try and figure out each one individually. The intersection of A and B, okay, with A and B, A is 6 and B is 2, 4 and 6. I hope you can appreciate that A is a subset of B. Can you see that? Yeah, A is a subset of B. So if we wanted to draw a Venn diagram with A and B, A is going to be on the inside, B is on the outside. It's 6, then 2, 4. And there are 6 numbers in total on the dice. So the probability of A and B is just that 6, because that 6 shares the event of being a 6 as well as being an even number. The probability of getting the intersection is 1/6. Then we're going to be dividing it by the condition that we've set, which is the number must also be even. So the probability of getting an even number when you throw a die would be 3 successful outcomes out of the total 6. So that's 3 out of 6. And then you can work this out. If you've substituted everything correctly with the correct numbers, all you do is take that division, rewrite it using a division symbol, 3 out of 6. Then you use your keep swap flip trick. That's 1/6 multiplied by 6/3. The 6's cancel out to 1, and the answer is 1/3. Okay, and you see that we get the exact same answer as before. I'd recommend that if you can use an easier method, do so, but being fluent with your formula is also very important. In example 6, 12 students play violin, 12 play piano, and 7 play both. Draw a Venn diagram and use it to find the probability that a randomly chosen student plays the violin, given, right, there's that reduced sample space part, given that they play the piano. They want us to draw a Venn diagram, so let's do that. We know that there's an overlap because some students play both, and I'm just going to label the events with their capital letters, V and P. Okay, let's populate this. I know that 7 students play both, fit that at the center. 12 students play violin. This is a question from the book. I got tricked the first time around, and I got the answer actually incorrect. When they say 12 students play violin, they actually mean 12 students play violin only. So let's just follow what the book does and write 12 here. And 12 play piano only. Okay, that's just a quirk of the book.
Would it be more clear than that on the exams and stuff?
Definitely. In fact, if it wasn't actually that, and you made a mistake on that, I'd argue with the exam marker.
Yeah.
With that one anyway. Okay, find the probability that a randomly chosen student plays the violin given that they play the piano. So, how do I write it? Given the piano like this?
The other way around.
Other way around, good. So the condition comes afterwards. The condition is that they must play piano, and the successful outcome is that they must play the violin as well. Okay, your reduced sample space isn't the total number of students now, it's just all the students that are playing piano. So the total number of students playing piano is 7 plus 12, that's 19. And the students that also play the violin, as well as playing the piano, is the number in the middle, 7. Okay, and if you'd like, you can label that this is related to the probability of violin and piano. This is the probability of just being piano. Okay. Question 8. So this is example 7, which is question 8 of your exercise. A group of 500 students were asked whether they would rather spend their recreational time playing sport or listening to music. The results, as well as the sex of the student, are given in the table. Okay, so this is like a two-way table, and you've got the totals at the end. One student is selected at random from these 500. Find the probability that a student prefers sport. There's no given in there. There's no restriction on these events, from what I can see. So there's no conditional probability. It's just the probability of randomly choosing a student that plays sport. Okay. There's no condition there, which means we must consider everyone in that group. And there are 500 students in total in that group. Do you ever notice that with most of these questions it's related to students?
Yeah.
Yeah. I think they're trying to relate to you guys. Anyway, the number of students that play sport would be the number that are also male and female. That's 375. And if you can see that 125 is a common factor between these, you can divide it out, and that's going to be 3/4.
So it's 120, isn't it?
Okay, this time we do have a conditional probability question. That's the given. So now it's the probability of picking someone who prefers sport, given that they're male. Okay, we can't consider all 500 students now. We are only looking at the number of male students. How many males are there?
300.
Yeah, 300. We've reduced our sample space, and out of those 300 students, I know that 225 do prefer sport. Okay, and if you simplify that, and if you can identify that 75 is a common factor, then the fraction also turns out to be 3/4. The current football fixture has the local team playing at home for 60% of its matches. When it plays at home, the team wins 80% of the time. I'll pause there and I'll re-say that question. When it plays at home, the team wins 80% of the time.
So given that they're at home,
Good, that's the condition. Even though they haven't said given, you're only considering the time when they're playing at home. So I'll just put this thing here. It's something you would highlight when you're doing a test as well. When it plays away, right, that's another condition. When it plays away, the team wins only 40% of the time. What percentage of its games does the team play away and win? So to work out this question, let's start by defining some letters for these events. Let H be a home game, which implies that H dash would be an away game. We also have winning or not winning, wins game, and I'll use W for that. And W dash, I wouldn't say lose, because you can sometimes draw as well. So I'll say not win. That includes the possibility of drawing. With these letters defined, I'm going to start writing down some information using probability notation. Okay, PRH, that's the probability of a home game. That's given in the first sentence, which is 60%. And that'll be 0.6. I'll use decimal notation. You can use fractions. It's down to you, which you prefer. When it plays at home, PR, that's the condition. So I'll write it down first. The team wins. The probability of winning given a home game is 0.8. So it's down to you to notice these conditions. The probability of when it plays away, so H dash, the chance that it wins is 0.4. Okay, so this is all the information that's given. And the question asks, and I'll write it in a different colour so you know what the question is. The question asks, what percentage of its games does the team play away and win? That and there tells me that both outcomes are occurring at the same time without any restrictions. PR, win, and home. I can actually write it as PR, home, and win. I can flip the order around, but I write it like this because I know all of my conditional probabilities have win and home in that order. Stay sharp. Was that your question?
Totally.
Okay. So let's start working this out. I'll probably start by writing out the equation that I know. And here's a big hint. It's the equation that I've got in blue there. That's the multiplication rule.
Yeah.
Play away. Oops.
Yeah.
Thanks for pointing that out. Play away. So I'll put a dash there and a dash there. Okay. So now this is correct. I'll write out my formula. So the formula is, if we've got the intersection, we write out its conditional probability and we multiply the probability of the condition. So I'll try and copy and paste it in the same way. We've got win given away game multiplied by the probability of an away game. So I'm looking at that multiplication rule, and right away I know one of its values. Obviously not the intersection, what we're trying to find. I know the first part, the probability of winning given it's an away game. Can you see? Yeah, 0.4 here. So I'll sub that in, 0.4. That's given. Here's the next one that we need to know how to get. The probability of having an away game. Michael?
Would that just be 1 minus the probability of of playing a home game?
Yeah.
Being 0.4.
Which is 0.4. So multiplied by 0.4. I'll rewrite it just so we know where this comes from. The probability of an away game is the complement of having a home game. You're either home or away. So this is where we got the 0.4 from. And 0.4 times 0.4 is 0.16. And we've got our answer. So at the end, you can write a general statement to answer this. 16% of the games away are, hold on, let's pause. Sorry,
10% of games away.
this is not right. Can you tell me why it's not right? It's the way I've worded the answer. Nikki, do you know?
16% of the games are won and away.
Are one and away. Because here, I've accidentally stated as another conditional probability, where I really should get rid of any conditions and say 16% of games are away and won. 60% of all games. Okay, adding that all in there reduces any chance of putting a condition.
If
Yep.
you did write it in the way that you wrote it before,
Yeah.
would it still be right?
No, I don't think so. It's so if you wrote it like that, I'd interpret it as you only considering the games that are away, which is a conditional probability.
But you're still considering only the away games.
16% of all games, whether or not it's played at home or away. Okay. I'm going to ask you to follow the questions for exercise 9F. 9F, that'll be questions 1 to 3, 5 to 7, 9 to 14, 16. So you need to make sure that you can identify when a question is based on conditional probability. Look for those words that are like given, and see if you can apply conditional probability and the multiplication rule to solve problems. This is 9F, continued. What we're going to learn is the law of total probability. It's just an equation that you'll need to know, but we're going to be seeing how we get that equation and why it works. So the success criteria is be able to apply conditional probability, the multiplication rule, which we've defined, and the law of total probability to solve problems. Okay, so let's start building up the law of total probability. First, we need to know what the multiplication rule is. This is in blue. So we're going to be using our blue equation to help us build the law of total probability. We're going to label it equation 1. We're going to put equation 1 here. The other equation is the intersection between A and not B. So in the same way, we can also write the expression using the multiplication rule. We're going to label it equation 2. All that's different is that conditional part, that given part. In this case, it's the complement of B instead of being B. Okay, we're going to put it there. Next, we're going to notice this little fact. The probability of getting an event A must be the combination of two parts. The part that's also in intersection with B, and the part that's just by itself. Notice the way I've written it. So I'll rewrite it up here. A intersection B, that's both parts overlapping, as well as A intersection not B, which really means A only. So I'll restate it. The probability of getting an event A is equal to this part in the middle plus that part on the side. This is equation 3. Notice, okay, the probability of A and B, we've defined it previously up here. I know it's blurry. The way you can write the intersection is using the multiplication rule. You can also use the multiplication rule to rewrite that other part as well. So this is all about substituting in equation 1 here and equation 2 here. And that's what's going to make your law of total probability. I'll state it out in words. Probability of A is equal to A and B plus A only. Adding those two parts gives you the entire circle. Okay, now we sub in the multiplication rule into this fact, and you get the law of total probability. Okay, it looks complicated, but the fact is, this is the intersection, which is really A and B. Okay, that's the first part. That's like your center of your Venn diagram. This part is A only, which is your moon shape of your Venn diagram. If you add those two together, you get your entire circle for event A. Now I'm going to rewrite this down at the board because this is a very important formula. The way we use this equation is just when the opportunity arises. So in our next example, before we get to that example, actually, diagrammatically, this is what it means. Okay, we're going back to our tree diagram. We've got event B happening first, event B or not B, as well as event A or not A. If we're looking at the possible outcomes that does result in A, there are two separate outcomes that result in A. So if we're trying to figure out the probability of A, we need to add those individual probabilities together. If you think about it, the probability of A, adding this part, A given B times B, plus A given B dash times B dash, that's actually just what our law of total probability is restating as an equation instead of a tree diagram. In a factory, two machines produce a particular circuit board. The older machine produces 480 boards per day with an average of 12% are defective. Okay, I'll restate that second sentence in another way to make it a bit clearer. 12% of the older machine's boards are defective. That's actually a conditional probability statement because we're only looking at the older boards. In the next sentence, they give you some information about the newer boards. or the newer machine. The newer machine produces 620 boards each day, of which, that's the conditional part, of which an average of 5% are defective. 5% of 620 are defective. A board is chosen at random and checked. Let N represent the event that the board comes from the newer machine, and D represent that the event that the board is defective. Okay, it's a lot to take, but fortunately the questions step it out bit by bit. So let's answer the first question. By the way, this is CAS, because it's asking 2 decimal places. PRN, the probability of selecting a board that is from the new machine. So the probability of selecting a board that's from the new machine is given by the fact that the new machine produces 620, the old machine produces 480, so we know how many boards there are in total. 1,100, right? So the sum of all boards produced in total is 1,100, is that right?
Yeah.
Yeah. And we're only interested in the machine that produces new boards because there are 620. Okay, so that would be the answer, and then you'd have to simplify it. That's going to be equal to 0.5636, and it just keeps on going. And then you have to approximate it to 2 decimal places, 0.56. I write the more accurate answer before my final answer because I'm going to be using this more accurate answer in the later parts of my question. Okay, so I'm going to keep it here. Next question, PR, D given N. That means, what's the probability of finding a defective board given that we're only looking at the boards produced by the new machine? The number's actually in the question. Can you see? 5%, right. Out of the new boards, 5% are defective. So let's just write that down, 0.05. The next answer is also in the question. The probability that the board's defective, given that it's not from the new machine. 0.12. Okay, so here's the part where we actually use some of our equations. Find the probability that if you choose a board at random from the entire pile, that they're both defective and from the new machine. Okay, how do you do that? Is there an equation we can use? Is it somewhere there? Yeah, what's it called? Multiplication rule. You can use the conditional probability formula, but it doesn't have the intersection at the front, so it's not clear right away that you can use this equation, but rearrange it a bit into the multiplication rule and you can use it. So let's plug in our values. It's PR, D given N, multiplied by PR N. And we've actually got all these numbers here already. So it'll be 0.05 multiplied by, and I'm going to use my more accurate answer to avoid round off errors. And that's going to be 0.0282. And it can get as accurate as you want. But I do include this more accurate answer because I actually am going to use it later on. But it does round to 0.03. Use that squiggly equal sign. Okay, that last question on the slide is actually very similar to the previous one that we've just done. I'll give you a moment to have a think about how we'd answer this.
Do we do the same thing, just instead of using D and N, you use the D and not N?
D and not N.
Yeah, and that's
exactly.
the same probability then.
And to find not N, which is just the complement, we just take this away from 1. So let's write that down, which is PR D given N dash, N dash, multiplied by PR of N dash. When I say N dash, it means not N. Let's sub in. We've gotten this first part from part 3, 0.12. we multiply it by the probability of not getting a board from the new machine, which is the complement of your first question that you did. 1 take away 0.5636. Okay, I'm using that more accurate value to avoid round off errors. That's going to equal to 0.05236, which is approximately equal to 0.05. So the probability of getting a defective board should be equal to the probability of getting a defective board, whether or not it's from the new machine. So the probability of getting a defective board from a new machine, okay, that's like the intersection part of your Venn diagram. And we add it to the probability of getting a defective board that's not from the new machine. Okay, that's the moon shape. And the combination of these two parts will make up your entire circle for the probability of D. And we actually have figured these out already in our previous questions. So it's just a matter of subbing them in, which is the result of 0.0282 plus 0.05236. And our answer, before we approximate, is 0.08055, which rounds to 0.08. The probability of getting a circuit board from the new machine, given that it's defective. So in other words, you've picked a board from the pile, it's defective, what's the probability that it's from the new machine? So this is an application of just the conditional probability formula, N and D, divided by what?
Probability.
So PRD, because that's our reduced sample space part. Now I've got those answers already. 0.02818 divided by 0.08055, which we got just before, and that's going to be equal to 0.3499, which approximately equals to 0.35. So that means if you pick a board from the pile and you know it's defective, there's a 35% chance that it must have come from the new machine.